In this video, I'm going to explain the basics of threads and parallelism in Rust, and we'll keep it short and easy, so let's get started. First, let's understand the difference between concurrency and parallelism. Concurrency is what I call as fake parallelism, where you just have a single thread, but we quickly switch between different tasks, whereas parallelism is where you truly have parallelism, where you have multiple threads, each working on its own task. And concurrency is generally used with IO bound tasks because IO bounds tend to be not so computationally expensive, so they live for a very short amount of time when they are being processed, and the delay is mostly caused because of some network issue or waiting for some API or due to network overload. So during this wait time, the thread or your CPU core can switch between different tasks and work on the task once is ready to be processed. So concurrency is just fast switching between different tasks, which just gives you the illusion of parallelism. Whereas parallelism is where you truly process multiple things at once. And because of this nature, concurrency is well suited for IO bound tasks which are short-lived on the CPU. Whereas parallelism is very good if you have CPU intensive tasks where each individual task takes longer time to run, like if you're doing some math heavy or some rendering related operations. And in this video we're going to look at parallelism in Rust. Here is how parallelism works in Rust. When you run your Rust code, you have an option to either run everything on the main thread or spin up multiple threads, which is what we're going to do in this video. And these threads are allocated to different cores which live within the CPU. And this is how at a high level parallelism works. Keep in mind that as a programmer, you only have control on the number of threads you can spin, and the operating system decides which core should be allocated for that particular thread. Operating system makes that decision depending on which one is idle and various other parameters that we don't have to be concerned with. So let's look at some code. I'm going to give you 7 demos, each with increasing order of complexity. Let's get started. Let's create a new Rust project with the command cargo new parallelism. Let's open this project in VS Code. We are only going to use the standard crate to implement threads in this video. Again, we have Rayon, which is a dedicated crate to easily implement parallelism, but we're not going to look at Rayon in this video because it's easy to use, it's more ergonomic, but you wouldn't understand how threads work. And you can also use Tokyo for the same, but we want to stick to the standard crate because that is how you truly understand how threads work in Rust. We don't need to install any crates because we're only going to use the standard library. Now, I'm going to set up some boilerplate so that it's easy for me to add demos. So first I'm going to create a new file called demo1.rs. And here I'm just going to have a function that I'm going to run in the main.rs file. And in the main.rs file, let's import this demo module. Mod demo, and use demo. This is just going to import everything. Demo 1. And when I do this, you can see demo 1 is currently not used and you get these unused warnings. So to avoid these warnings are really irritating and they distract from the main topic. So I'm just going to use allow unused macro so that you won't be bombarded with these warnings. Now it looks clean. I'm just going to call the demo function in the main.rs file. That's it. Now we'll go ahead and implement the code in our demo file. Okay. So we can use the spawn function inside the thread module of the standard crate to spin up a thread. And in the code, we can just call the spawn function and call the join function to just wait for the thread to execute. And inside the spawn function, we can pass a closure. A closure is nothing but an anonymous function, a nameless function. And here is how you define a closure with 2 pipe symbols. And then I'm just going to put in a print line statement that this is running inside a thread. And that's it. Let's hit save. If we run this with the command cargo run, you should see that this is running inside the thread. But it's not really apparent, right? You don't understand, is it main thread or is it a sub thread? So let's add some logs to understand this. Let's add a println statement before and after the spawn function and let's see what happens now. First we get the CPU spawning the CPU task, then we get the code that is inside the thread, and then all threads are closed. It's still not apparent. It's still running in the same sequence, right? So it doesn't really show you whether it's running in parallel or not. So what you can do is you can extract the handler from the spawn function instead of calling it directly. So let's do that. So I'm going to say let thread handler is equal to and remove the spawn later. Sorry, the join function after that. And this is going to return thread handler of type join handle. Then I'm going to put a simple print line statement that we're waiting for the task to complete. And after that, I'm going to call the join function. All right. Now we should first see the spawning of the CPU task. Then we are just waiting for the task to complete. Then we should see the code inside the thread, and then all threads are closed. So let's run it. So first we see spawning CPU task, then we see the third print line statement, and then the code inside the thread, and then all threads are closed. So this works fine. So this is how we can extract the thread handle and make it wait by calling the join function. And this is just a basic demonstration of a thread. Instead of passing a closure, you can also create a function and pass it inside the spawn function. So let's do that. I'm going to create a function called task. It is going to have the same print line statement. And then we can pass this task function instead of a closure. So let's save this, and if we run it again, we should see the same result. That's it. So that completes demo 1. In this demo, let's implement multiple threads. We are discussing about threading, right? So it makes no sense to just have a single extra thread. So let's implement 2 threads. So I'm going to clone this demo file, demo1, and call it demo2.rs. And inside my main file, I'm going to point to demo2 instead of demo1. That's it. And inside the demo2, I'm going to call th1 as my first handle, and I'm going to create a second handle called th2. And below that, I'm just going to await is applicable for concurrency, but here we're just going to join these two individually, and this is how we wait for both the threads. So let's run it. You will see that the logs in the right sequence. So first spawning the CPU task and waiting for the task to complete. Then after both the threads are finished with execution, we get the message that all threads are closed. But it doesn't really tell the difference which one is executing first, right? Like I said, the operating system decides which core is allocated to the thread. So the sequence is not necessarily guaranteed. So what I mean by that is even though you're calling th1 and th2 in the sequence, it's not necessarily true that these two will run in the same sequence. So I'm going to add some logs to demonstrate that. So I'm going to call this task1 and call it thread1. And I'm going to create another task called task2 and call it thread2. Okay. And inside this, I'm going to call task1 first and task2 in the second handle. Okay. Now if we run this, let's see what happens. All right, you see thread 1 and then thread 2. Let's run it again. Thread 1, thread 2, thread 1, thread 2, thread 1, thread 2. All right, you see this thread 2 and then thread 1. So this is one of the pain points of parallelism. So the sequence is not necessarily guaranteed, which is something that you have to take into account when you implement parallel code. Okay, let's move on to the next demo. As always, I'm going to clone this to demo3.rs, and in my main file, I'm going to point to demo3. Okay. In this demo, instead of just spawning 2 threads, I'm going to create a vector that holds multiple threads, and we're going to join all of them at once. So first, I'm going to delete task 1 and task 2 and just call it task. And I'm also going to delete the thread 1 here. Then I'm going to create a vector, call it threads. I'm going to make it mutable because I need to push the threads later. And then I'm going to create a thread count because we're going to have 10 threads. And again, there is no limit as to number of threads that you can spin. Then I'm going to create a for loop to just add tasks to that thread. And then we're just going to add a log statement to just wait for the task to complete. And then we're going to join all the threads, and that's it. And after that, all the threads are closed. Let's hit save. All right, that looks good. Let's run it. Let's hit cargo run. Awesome. So this is how you can spin multiple threads using a vector instead of individually defining each individual thread. Let's move on to the next demo. I'm going to clone demo 3 and call it demo 4. And also in the main file, I'm going to point to demo 4. In this demo, I'm going to implement a CPU intensive task, and I'm going to show you how the main thread waits for the task to complete, and then after the thread is completed, we're just going to close the thread and return back to the main thread. So I'll show you that clear delineation. So first I'm going to change the task function. Instead of returning a simple printline statement, I'm going to implement a computationally expensive function that loops around 500 million times and returns that the task is complete. Because we need a task that takes a while to process, okay, so that I can show you the difference between the main thread and the thread that is running in parallel. Then I'm going to delete everything inside the demo function except the first print line statement. Then I'm going to create 2 handlers for these tasks, and then we're going to put a print line statement that we're waiting for the task to complete. Then we're going to have a loop that is going to run continuously and show you the difference between the main thread and the child threads. So in the loop, we're going to have a print line statement that is going to run on the main thread, and this print line statement is going to run until the threads are complete. So after the loop, we're going to use, instead of join, we're going to use isFinished. isFinished is a function that returns a Boolean value which tells you whether the thread is finished with the processing. So we can use the status 1 and status 2 and break the loop. Okay, so let's run this. If we run this function, we should see this print line statement, threads are grinding, to show up continuously until the task is complete, and once both the tasks are finished, we should break the loop. So let's run this. Awesome. So you can see the threads are grinding, and then after a few seconds, because we have a loop of 500 million, right? So it takes a while to process. Awesome. So after the tasks are complete, then we can see the control return back to the main thread. I'm going to add an extra thread here. Extra print line statement that all threads are closed. Let's run this again. It's going to take a while to process. Awesome. So once all the threads are finished with the processing, we see the message, all threads are closed. Perfect. Let's move on to the next demo. Let's clone demo 4. Call it demo5.rs. And inside the main file, I'm going to point to this demo 5. Okay. I'm going to delete everything inside the demo function except the first line. And what we're going to do is, instead of hard coding the limit here, we're going to pass the limit from the demo file. The demo function. Okay. And we're going to see how the scoping works, how we can define a variables in the demo function, and is the scope still valid inside the task function which is running in its own thread. Let's see if that is the case or not. I'm going to change the task function to accept an input called limit, which is of type U64, and we're going to remove this hard-coded 500 million value. That's it. Alright, we see a mismatch that this is of U64 whereas X is of type U128. So I'll just change this X value to U64, and that should be good. Now let's create a variable called a limit which holds 500 million. Then we're going to create a handle to pass the task function inside the spawn function to create a thread, and we're just going to join to wait for the thread to complete. Now we just pass the function definition when we call the spawn function, but how do we run it? By passing the limit limit argument, right? The easiest solution you can think of is to pass a closure, because that allows you to pass arguments, right? So let's pass the limit argument and hit save. Now we run into an issue. I have this VS Code extension that gives me compilation errors, but let's run this so that you can see the message more clearly. So when you pass the closure here, we see that this thread may outlive the value limit. So because this limit lives inside the main thread and we're spawning the task inside a child thread, the limit variable this is going to outlive, this thread is going to outlive the main thread. So we cannot do, this is not allowed. So what Rust suggests is to use the move keyword to pass the ownership of this variable to the child thread to get rid of this issue. So let's follow the recommendation of the Rust compiler, and that seemed to do the trick. Let's run it. Awesome. So now we didn't see any error and looks like the child thread finished with execution. So this is how you can pass arguments to the child thread by using the move operator and passing a closure to transfer the ownership. Let's move on to the next demo. As always, let's clone this and call it demo6.rs, and in the main file I'm going to point to demo6. In this demo, let's return a value from the child thread and log it and process it inside the main thread. So you might have threads that do some computationally expensive task, and those tasks can return some results that we want to capture. So let's see how to capture those. It's quite simple. I'm going to upgrade the task function to return a value of type u64, and instead of just a simple printline statement, I'm going to return x. And again, if I don't put a semicolon after x, that means that the value is being returned from the function, or you can say return x. These two are the same, but to keep it simple, I'm just going to say x and exclude the semicolon. Okay. Then I'm going to add a printline statement that we're waiting for the task to complete. Finally, we can capture the result by assigning the values of join function to a variable. So let's say total is equal to ts.join. That means the value that is returned from this thread is being passed on to the total variable. Okay. And finally, let's print this value. It's going to return a result. So I'm going to call expect to extract the value from the result, and that's it. That also allows you to pass some message if the thread panics. So to handle error cases, I'm just going to say task panicked. Let's run this. Spawning CPU task, waiting for the task to complete. The task is complete, and then the value is, this huge number. So that's it. So that is how you capture the results back from your child thread. Let's move on to the final demo. So I'm going to clone this, call it demo7. And also in the main.rs file, I'm going to point to demo7. In this function, let's expand on returning the results. So in this case, we are just returning a simple u64, but ideally, you might have some errors inside the thread. The thread can panic at any step, right? So you want to return, instead of returning u64, you want to return a result that returns the value or some error, which we handle in the main thread. So let's do that. Instead of updating a simple u64 value, we're going to return a u64 or a string so that we handle the error cases as well. First, we're going to do some validation. If the limit value is greater than 500 million, we're going to throw an error that the limit is too large to handle. Again, just to demonstrate how we can implement errors or exceptions inside the child thread. And finally, instead of just returning x, we just return OK of x. That's it. Finally, we need to replace, instead of just printing total, we cannot just extract total here. We need to use a match function to extract the values. So once we wait for the join, we're going to get a result. So we'll handle three cases, right? Either it's u64, we get the value properly, then we say the task is complete, or we get the exception inside the child thread, which will handle in the error case, or the thread panics, right? So that we handle in the main error case itself. So this allows us to handle all the possible scenarios. Let's run this. This should run fine because we have the value set to 500 million. But let's change it to 500. We'll just add 1 to demonstrate, the exception inside the child thread. And I'm going to run this in quiet mode. And these compiling, finished and running, they are very annoying. So I'll just run it in quiet mode. And as you can see, the task failed because the limit is too large for the task to run. Awesome. So that's it for this video. So this is how you quickly and easily implement threads using the Rust standard library. One thing we haven't covered is how we can implement communication between the threads. So that deserves its own topic. Again, there is so much to talk about. There are two predominant methodologies and on how to communicate between threads. One is where you define some state and let both the threads access the same state. This is called shared state. The other technique is to pass data between the threads, which is called send messages. So these are the two popular techniques. One is shared state to communicate, or communicate to share state. So yeah, that is quite exciting. Like I said, each of these methodologies require their own topic, their own video. So we'll cover that in subsequent videos. Again, in real world, you might not be using the standard library. You might use Rayon or Tokyo to implement threads. But the reason I want to spend some time and do it with the standard library, because I want to understand the basics. I want to, be good with fundamentals so that you appreciate what these crates do for you. So if you want granular control on a particular project that you're working on, right? If you want fine-tuned control, you can, now that your fundamentals are strong, you can implement the right technique that best fits your, project requirement.